A dietitian is planning a snack package of fruit and nuts. Each ounce of nuts will supply 0 units of protein, 2 units of carbs, and 1 unit of fat, and will contain 20 calories. Each ounce of nuts will contain 3 units of protein, 1 of carbs, 2 of fat, and 30 calories. Every package must provide at least 6 units of protein, 10 units of carbs, and no more than 9 units of fat. Find the number of ounces of each that will meet these requirements in the fewest calories. And how many calories will this end up being? Okay, so the same as the previous examples, we'll start off by first figuring out what our variables are going to represent. And you can see this kind of gives us a giveaway. It says find the number of ounces of each of the two types of snack, of each of the ingredients, I should say, that will be used to meet these requirements in the fewest calories. So the number of ounces of fruit, I'll go ahead and call X, and the number of ounces of nuts, I'll call Y. Now, kind of looking ahead, the fewest calories, this is telling us what our objective function is. So when I'm reading through this, the calories are going to tell me what that is, what my objective function is. I could actually write this down at any given time. So the fewest calories, well, Z is equal to, I get 20 calories per ounce of fruit, so 20 times X. And I get 30 calories per ounce of nuts, so this will be 30Y. That's my objective function. I'll come back and use that when I have my feasible region all figured out. But really, I kind of need to start off with, once I figured out my variables, the next thing I really need to do is to do my constraints. So when I see things like this, it needs to contain at least 6 units of protein. That sounds like a constraint to me. Sounds like it has to be at least 6. So something is bigger than or equal to 6. And that something is the amount of protein that's contained. So each ounce of fruit contains 0 units of protein, so 0x. And each ounce of nuts contains 3 units of protein, so 3y. Of course, this equation could be simplified. That part just goes away. This is just 3y is greater than or equal to 6, or y is greater than or equal to 2. And actually, it's kind of handy as far as graphing. That's how I'd prefer to look at that one anyway. That's a protein constraint. Every package must contain at least 10 units of carbs, so that is a separate constraint. So carbs, something needs to be bigger than or equal to 10. Well, let's see, each ounce of fruit contains 2 units of carbs, so in total, from the fruit, we're going to get 2x carbs, and from the nuts, we get 1. So 2x plus 1y is greater than or equal to 10. And then no more than, each container must contain no more than 9 units of fat. So fat is another constraint. Except you'll notice I said each of these said at least a certain amount. Well, this one we say no more than 9 units of fat. So it's less than or equal to 9. But other than that, it's kind of the same. It's 1x plus 2y, because the 2 ounces of fat there. Those look like all the constraints that are mentioned here, but of course we can't have a negative amount of fruit or a negative amount of nuts, so that's why we'd say x and y both need to be bigger than or equal to 0. Alright, for graphing this, I want to figure out what the intercepts are. This is a horizontal line with y coordinates equal to 2. That's easy enough. This one right here, if the x coordinate is equal to 0, I get the y is 10. And similarly, if the y coordinate is 0, I get x is 10. On this one, if the x coordinate is 0, I get 2y equals 9, or y equals 4.5. And if the y coordinate is 0, I get x equals 9. So I get 9, 0. Let's see, as far as shading is concerned, well, I'll do that in just a second. Alright, so graphing all of these, it looks like I just need to go up to 10. So let's go 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Alright, y is greater than or equal to 2. That is a horizontal line right about here. And shading on this one, I would want to shade above this line, because y is bigger than 2. You can do your standard test point thing if you want, or just think about, okay, where is y bigger than 2? It's when we're above the line. Alright, 0, 10 is the next line, the intercept of the next line. I'll go 5, 0, which is over here, and draw that line in, so we get this. Let's test the origin here. 0, 0. 0 plus 0 is not greater than 10. Go figure, if we don't have any fruit or any nuts, we're not going to have enough carbs to meet this requirement, so we want to shade away from the origin here. And for fat, let's see, we get 0, 4.5, which is about here, 9, 0, which is over here. Draw that line in. Looks about like that. And if we test the origin here, oops, test 0, 0. 0 plus 0 is less than 9 is true, so we'll shade toward the origin on this one. So it looks to me like, so that's line 3. Let me just draw a little zoomed in version here. We have line 2 looking like this, line 3 looking like that, and line 1 looking like this. 1, that's unclear. Let's go 1, 2, and 3. Those are the lines. And our feasible region here, it looks like should be this region right here. So I just kind of did a zoom in. This is our feasible region, and these 3 points are our corner points. So we need to figure out what are the coordinates of those 3 corner points. So right here, we're at the intersections of line 1 and 2. The intersections of lines 1 and 2, I'm going to have to do, it looks like I'm going to have to actually do this the hard way for all 3 of these. So I'll pull up the matrix, and line 1 is 0, 1, 2, just y equals 2. Line 2 is 2x plus 1y equals 10. And when I run RREF on this, on matrix A, I end up with the point 42. Redo that. There we go. So that's the point 42. Let's do lines 1 and 3. So pulling out the calculator again. Line 1 is already in there. Oops. Line 1 is already in there. It's 0, 1, 2. Line 3 says 1x plus 2y. Oops. It's a 2 by 3 matrix. 1x plus 2y equals 9 is what line 3 says. So when I run RAF on that, I get the 0.52. And the intersections of lines 2 and 3, that's this point right here. You can see there's line 2, line 3. Let's go ahead and figure out where that is. 2x plus 1y equals 10. Run REF on that one. We get 3.6 repeating and 2.6 repeating. I'll go ahead and round those off to fractions. 11 thirds and 8 thirds. Or I suppose you could say 2.6 repeating. Yeah, maybe. Whatever. Was that right? 3.6 repeating. And 2.6 repeating. There we go. I guess it doesn't really matter how we write that. Unless the computer asks us to put it written as fractions. Alright, in any case, so the whole reason we found those corner points is so now we can test the corner points with our objective function. So first off, 4, 2, 5, 2, then 3.6 repeating, 2.6 repeating. Our objective function was 20x plus 30y. So I get 80 plus 60, which is 140. And actually, I could just plug all of this stuff into the calculator. I don't need to... I just realized I wrote that wrong. I don't need to do this by hand, I suppose. So we get 100. It's hard not to do some of this multiplication. Whatever. 100 plus 60. And then lastly, this 3.6 repeating. 3.6, just throw through a few sixes on there, times 20 plus 30 times 2.6 gives me 153.3 repeating. Now this of course doesn't actually say 3 repeating here, it ends in the 2, but that's hopefully pretty easy to see why that is. It's because I stopped writing, and so I rounded, which caused it to round. In any case, that's neither a minimum nor a maximum, so that's actually, I don't really care about that point. This point right here is the one I do care about. This is my minimum. Because what we're asked to do here, find the number of ounces that will meet the requirements in the fewest calories. So I wanted the smallest number of calories. And it looks like if you do 4 ounces of fruit, 4 ounces of fruit, 2 ounces of nuts for 140 calories. And I suppose I probably should have wrote calories with a capital C to make all those nutrition people happy.